during the break, I could spend a little bit of time and tell you a few things. So first of all, question that is interesting that came up is how severe is the fermion doubling problem? And I would ask you, I will tell you that the fermion doubling problem is very severe for two reasons. First of all, as you know, QCD is asymptotically free if you have sufficiently small number of flavors. So if you manage to get too many flavors, then you will basically lose asymptotic freedom. So that's pretty severe. So if you had flavors that are not the amount that you want, then the running of QCD coupling constants will be altered at the very least. So the second thing is that is important is if you have fermion doublers, this additional light degrees of freedom will mix with the regular light degrees of freedom you want to have through gluon interactions. Because if you have, as I have here, if you have a, let me write here then, if you have a fermion that comes in with some low momentum and you get a gluon which has a high momentum, then it will remerge out with as a fermion with a high momentum, but this would be a light degree of freedom of a different kind, one of the doublers. So you have this peculiar situation where these flavors, these additional flavors that you have, they mix through gluon interactions, which is not a property of QCD. QCD flavors, the up quark remains an up quark no matter how many gluons hit it. So these are two, I don't know, important problems that you will face if you don't have the right number of flavors, or if you preserve these doublers into your spectrum. So there are many other kinds of fermions that you could hear about, and I'm not going to get into details. So the first kind I would write down as they're called as Clover fermions. And sometimes are called Seikoslami-Wohler fermions that I'm not going to write down these names because I complicated. So if you go to Europe, they will call them Seikoslami-Wohler fermions because these are Germans and they know how to pronounce their names. And in the US, they are called Clover fermions. The reason that they are called Clover fermions is because they, okay, I'm not going to get into why they're called Clover because it's a nice word. So what are the Clover fermions? So the Clover fermions is, let me write it this way. You have the Wilson fermion action and you add to this fermion action a term that is as follows. It has a coupling constant that is like this, CSW is called. It has a sigma mu nu and the F mu nu. And if you ask the question, how do I write down the F mu nu? On the lattice, you saw, take the plaquette, the leading term, the imaginary part of the plaquette is F mu nu. So I remind you, I had here, here you take the plaquette, you expand it out, the leading term, the imaginary part of the P mu nu is F mu nu. So you can write down, and so this additional term into the action, as you can see, is a dimension 5 operator. You see, if you count the number of lattice spacing powers that comes with it is 5. And so from the point of view of the continuum field theory that you have learned, dimension 5 operators are irrelevant, as they are called. So they don't change the universality class, the continuum theory, by adding these additional operators doesn't change. It is the same. But this dimension 5 operator is added with a coefficient here that is tuned in such a way that the leading lattice spacing errors are canceling. So fermion, the Wilson fermion has, if you ask the question, how do observables approach the continuum limit if you do a Wilson fermion calculation? They approach with order A corrections. They are linear in the lattice spacing. So Clover fermions, they tune this coefficient so that the leading lattice spacing error becomes order A square. So if you performed a mass of a nucleon calculation, let's say, and we will learn how you do that, and you plot it with respect to the lattice spacing, you do a calculation like this, and you will find that the nucleon mass extrapolates to the continuum limit linearly in lattice spacing squared with Clover fermions. Now, if you do the same calculation in Wilson fermions, and there would be some error bars because it's a calculation, it's a Monte Carlo calculation, you will find that the approach with A, so in the plot of A squared, it looks like a square root Wilson fermions. So these so-called Clover fermions that are popular in lattice calculations are designed in such a way that remove the leading lattice spacing error from Wilson fermions and make the errors that you have, or the approach to the continuum limit, to be linear in A square. So these are the class of fermions that are called Wilson fermions. So Clover is, in these days, is the state of the art. All lattice calculations that are done with Wilson fermions, they're using the Clover variant of Wilson fermions. And this coefficient here, C, is determined non-perturbatively, actually. You can determine it in perturbation theory, but you can also determine it non-perturbative by defining a condition which eliminates these order A errors. Now, there are more varieties of fermions, and I will list them. There is the so-called Kogot-Susskind fermions. So the Kogot-Susskind fermions are a class of fermions that try to embrace the doubling problem. So if you have naive fermions, you have 16 degrees of freedom, 16 light degrees of freedom. The Kogot-Susskind formulation does two things. First of all, it diagonalizes the spin matrices and you eliminate the spin degrees of freedom. So you divide your original number of flavors by 4. So you are left now with 4 flavors to deal with. And you say, okay, 4 is not that bad. It's not that far away from 2 that you want in light degrees of freedom. And it's basically, if you include the strange quark and the charm quark, now you have 4 flavors. So it's okay. So we will live with them. And these 4 flavors now have this problem that they have this mixing with high momentum gluons, and you have flavor symmetry breaking. And in the end of the day, you can improve that, remove a little bit of this flavor symmetry breaking, and you can have a very consistent formulation of the theory that is much cheaper than Wilson fermions computationally, and but you have to live with this problem of 4 flavors, which you have to perform some additional tricks to eliminate it, that's the 4 down to 2. So The next class of fermions that exist is the so-called, I will write them, sometimes they're called chiral fermions. So these are lattice discretizations of the fermionic action that do not preserve the continuum chiral symmetry, but they preserve a different lattice version of chiral symmetry, which I have written here due to discussions in the during the break. So there are two types of those chiral fermions that are used in today's simulations. They are the domain wall fermions. And this is the other one is called the overlap. So these two are very much related to each other. So the domain wall fermions, they work on a five-dimensional space. This is a fifth dimension. And the QCD lives only in the 4 dimensions, so the gauge fields are 4-dimensional. There is no gauge field along the 5th dimension, so there is no way 5, let's say. There is no way 5. And the formulation of those, there is a boundary. In 5th dimension, the space is not periodic. It has Dirichlet boundary conditions. And it turns out that domain wall fermions localize, let's say, localize exponentially on the wall, the right components of the Dirac spinor and the left components. As you know, the Dirac spinor is built out of the left and the right spinor. So it is a 4-component, 2 degrees of freedom are left fermions, and the other ones are the right fermions. And these two parts of the Dirac spinor are localized on 2 different walls, the 2 different boundaries of this 5-dimensional space. And if you, so this is how they basically avoid Nielsen-Nomilla theorem by having a non-local theory in 5 dimensions. So half of the spinor is sitting in one place, the other half of the spinor is sitting in another place. Now, this domain wall fermion picture can be actually written in terms of 4-dimensional degrees of freedom by integrating out the degrees of freedom that live in the 5th dimension. And integrating out these degrees of freedom lead to your overlap fermions. And the overlap fermions is a 4-dimensional formulation of QCD that has this remnant chiral symmetry on the lattice that gives you massless fermions when you have quark mass to 0 and avoid the fermion doubling problem. So these are all the types of fermions. Now, if you ask the question, what kind of discretization errors you have in the case of staggered fermions, here you have order A square errors. In the case of domain wall and overlap, you also have order A square errors. And in terms of who is more expensive, computationally, these guys are cheap, while these are expensive. Actually, very expensive. Now, Wilson fermions is the middle ground, and in fact, it's a very good way of doing QCD calculations numerically. Okay, so I'll stop here, and I don't know if you have any other questions about this general formulation of QCD on the lattice. So now, if you don't have any other questions, let's try to go and discuss how you actually do computations. So we will have to write down our partition function, z, which is an integral, and with respect to the gauge fields, it is an integral. With respect to the fermion fields, an integral. And then this is weighted by the gauge action and the fermion action. Now, as we discussed, the fermions are Grassmann numbers. And I assume that you're all aware about this fact. Grassmann numbers are anti-commuting variables. So what does it mean to integrate over Grassmann numbers is a complicated question. And but we know how to do it, at least operationally. And we know that if I integrate over Grassmann variables that I have here, what happens is that I get a determinant of the Dirac matrix that described my fermion action. And then I get e to the minus s gauge. So I can get rid of the fermions by integrating out the Grassmann variables. And all I do is I get a determinant, the fermionic determinant, to be sitting over there. Now, what happens in the case of computing expectation values? So if I want to compute any correlation function, I would have to do 1 over z integral du, and I have integrated out the fermions, and what happens is, and I will write a formal expression, I will put a hat here, u, and then I have the determinant of d plus m e to the minus sg. So first of all, let's forget about the hat that I wrote here and look at this expression here. So if I can tell you that the determinant of d plus m, or of the Dirac matrix, is positive, it's a positive number, then the gauge action up there is a positive, it's a real number, the exponential of a real number is positive. So we can treat this as a positive weight. So it resembles statistical mechanics, where you have a particular probability for certain states to appear that is given by the Boltzmann weight. In this case, the gauge action looks like a Boltzmann weight. And if the determinant is positive, then you can always interpret it as a Boltzmann weight. So in order to calculate these quantities, we can use statistical mechanics methods. And those methods are usually going by the name of Monte Carlo simulations. Now, what is the O hat that I wrote here? The O hat, this should raise. The O hat of U is what's left in the case of a correlation function that is made out of fermions. For example, if you want to calculate, if we only look at fermionic degrees of freedom, and you have d psi bar, e to the minus psi bar, m psi, where m is just a matrix up there, and you want to calculate psi bar x, psi y, it turns out, and I'm not going to, I don't know, derive this, it turns out that this becomes the determinant of the matrix M times the M inverse evaluated between the points of x and y. Actually, maybe I should be more careful about the order of the indices, y and x. So if I had a correlation function that had the psi bar and psi involved, every single pair of psi bar psi, after I integrate out the fermions, is going to be replaced by the inverse of the Dirac matrix. And the Dirac matrix is this D plus M that defines the fermion action. So with this in mind, we know that if I want to calculate any correlation function in QCD, I can treat it as a statistical mechanics problem and calculate the path integral by sampling this positive weight that I have here. So this technique is called the Monte Carlo integration, and it is a general technique that you can find as a method of calculating integrals, high-dimensional integrals. It's a terrible method of calculating integrals, but it is the only method that you can calculate integrals of very high dimension. So if you're trying to calculate a one-dimensional integral, you are better off doing your trapezoid rule or Gaussian quadrature. If you go to 5, 6 dimensions, then these straightforward numerical techniques that you know, they begin to falter. And if you go to a very high dimension, which is what we're talking about in QCD, you will find that there is no way of calculating integrals. The dimensions that we are talking about here are in the billions. They are not 1 or 2 or anything. So before I move on, I'm not going to spend too much time about how this integration works about. And I'm only going to write down a very simple formula. So if I am calculating an expectation value of some operator O, and I will write for the moment in one-dimensional integral, my weight, my Boltzmann weight, which is the gauge action multiplied by the fermionic determinant, is going to be given a probability distribution, P of x. So let's go back here and say that I will treat the probability distribution P of u as my determinant of E plus M times e to the minus s gauge of u. So this is times du. So this is my weight in this integral, which is positive. And I can argue why it is positive. The determinant is positive, but I'll do that later. For the moment, let's not worry about it. So this is my probability weight, and the way that I can do this integral is by sampling the gauge configuration space with this particular probability. It's times 1 over z here. I'm sorry. So now it is properly normalized. P of u is a probability distribution because it's positive and integrates to 1. Okay, so to come back to the simple example, so all that we are trying to do here is evaluate something that is of that sort. And let's put boundaries from minus infinity to infinity. And P of u is positive. And if I integrate over all the domain, P of u is 1. So P of u is the term is a probability distribution. In our problem, this probability distribution is a high-dimensional probability distribution. In this simple example, it is a one-dimensional example. So since this is a probability distribution, it's not very difficult to imagine that the expectation value that I have to do, because this is like, it's an expectation value, it's a probability distribution multiplied by something. So that's the definition of the expectation value of that observable. Then this is going to be nothing but, you can estimate it by sampling the probability distribution and evaluating this average. So that's what we're going to do. That's a simple statistical mechanics type of argument. This is exactly what we can do in the case of QCD. I have a probability distribution, P of U, which I can sample, and I can calculate O of U as an expectation value of this guy evaluated in configurations that I generate by my probability distribution. So if you ask the question how quickly this technology works and what is the error, this is a statistical estimate. The error is going to be given by the standard deviation of the mean. And the standard deviation of the mean, as we know, converges as 1 over square root of n, where n is the number of samples. Why is that? It's because the error, if let's call it error, is the sum over OXI minus the expectation value of xi of x. That's not, doesn't have an I, squared. So that's the variance. And then we take the square root of that, 1 over n. That's called the variance. And then we take the square root of that and divide by the square root of n. So that is the error of the mean. Now, the variance and the standard deviation, which is written up here, is a property of the probability distribution that I'm talking about. It's a constant. It doesn't matter how many samples you're using. It's a fixed number. So the error, which is the standard deviation of the mean, has this additional 1 over square root of n term, which is getting so that the error becomes smaller and smaller as you increase the number of samples that you're doing. So anything that we compute in the Lattice QCD with this technology is going to have an inherent statistical error that comes from the sampling of the distribution. Now, so I usually like to give you a, no, I'm not going to do that. So there are many methods of how I'm going to, how one can simulate QCD and how one can generate configurations with particular probability distribution P of x, or in this case of our QCD partition function. So these methods are going under the name of Markov chain Monte Carlo. And I will write the name here so that we see it. Markov chain Monte Carlo. So the Markov chain Monte Carlo is a method with which you start from one configuration and you perform a transition. So you start from some x0 and you perform a transition from x0 to x, and you get x1. And this transition is a probabilistic transition that depends only on the current state. And then you perform the same transition and you get x2, and you so on and so forth. So Markov chain is a process that updates itself. It goes from one state to another state, and this update procedure is only depending on the current state. It does not depend on the previous or in the future. So that's the definition of a Markov chain. And it turns out that if you choose this transition probability T appropriately, you can prove that the configurations that you generate this way converge to the probability distribution that you want. Now, I will write down the basic condition for having that property in the Markov chain Monte Carlo. This condition is called detailed balance condition, detailed balance. So if I'm trying to generate configurations PU that satisfy probability distribution PU, and I have a transition probability T from U to U prime, then if I can show that the following property is satisfied, PU prime of TU prime to U. So this is called detailed balance conditions. If this is true, then the process, the Markov chain Monte Carlo, converges to P of U. So the mental image that you have to have is that you start with an ensemble which has a probability distribution Q of U, and you perform the Markov chain Monte Carlo, and this ensemble will converge to a new ensemble which has probability distribution P of U, which P of U is the distribution that satisfies the detailed balance condition. So this transition probability defines the algorithm, and this is the probability distribution that you want to generate. And by performing the Markov chain Monte Carlo, going from one state to the other many times, you get to the target probability distribution. Now, this is a general procedure that is applicable to many statistical mechanics systems. If you have done statistical mechanics, you might know the Ising model. It's a classic example for phase transitions that is studied in statistical mechanics, and one can simulate it, for example, with these Monte Carlo techniques. So let me see what I can do here. I don't know, maybe if you want to lighten up a little bit how does the laptop is visible? And I have to share the screen. No. Yeah, okay. So I'm not going to do. I'm not going to. Let's forget it. Yeah, but doesn't matter. It's not. I think I'm not going to spend too much time on the Monte Carlo methodologies because it's too complicated for us to talk about. Now, let's assume that we know how to do the simulation. It's could spend the whole lecture talking about how, or the very basic things about these simulations. Let's assume now that we can do these calculations, we can do these simulations, we can generate configurations with arbitrary probability distribution that is that defines QCD, and we now want to calculate something useful about QCD. So what is useful about QCD? So one thing that you might want to calculate is masses, computation of masses. This is a most basic thing that you would do in a lattice QCD calculation. So in order to calculate the spectrum, we'll go back and figure out how do I, so let's assume that I have a vacuum expectation value, a vacuum expectation, and I have an operator that acting on the vacuum creates a state, and I have another operator that acting on the vacuum at some different time t annihilates the state. And I want to calculate the mass of the pion, let's say. So I need to have an interpolating field, an operator O dagger that acting on the vacuum generates a pion state. And then I want to let this pion state propagate for a period of time and then see what happens and then annihilate it. So the first thing that I have to do in order to calculate this, I have to convert it into a path integral. I have to write an integral over d psi bar, du, and then I have to put these operators here, dagger at 0, and then weight it by my action. Now, what kind of operator can generate a pion out of the vacuum? It has to have, at the very least, the quantum numbers of the pion. And it actually, the only thing that I need to have is an operator that has the quantum numbers of a pion, because if it acts on the vacuum and it generates an arbitrary state with the quantum numbers of the pion, then this arbitrary state contains the pion that I want. Okay, but now you might ask the question, how am I going to get to the ground state, which is the physical pion, the lightest particle in this sector? Fortunately, the Euclidean space comes to our rescue. But let's first work out what is this interpolating field that generates a pion is. So if you write down an interpolating field that for any meson actually, and I will write it as O of x, no, I don't care about any space-time location. Let's see this. So for any meson, and I will put the letter gamma here, then I can write something that is q bar gamma q f prime sum over all the flavors that participate in this generating this meson. So this gamma is a matrix that is built out of flavor and spin degrees of freedom. So for example, so if I want to do the pi plus, so you can have a u or d bar gamma 5 u. So that gives you a pi plus. It has the right flavor content and it has the gamma 5. The gamma 5 in there, you realize that this is a scalar. It has angular momentum 0. And in terms of parity has negative parity, and in terms of charge conjugation, it has a positive charge conjugation. So this object here transforms under chiral symmetry and rotational symmetry the same way as the pion transforms. It has the quantum numbers of the pion. So the candidate for this omega, this O that will generate a pion out of the vacuum can be written out in terms of quark fields this way. So because these kinds of correlation functions has 2 points, they're called 2-point functions. So the 2-point function for the pion, which is a function of due to translation invariance of a single variable t, which is the separation of the creation and annihilation operators, can be written as in terms of a path integral, d psi dagger, du, and here I have the d gamma 5 u, okay, u bar gamma 5 d, and this is at some point 0, and this is at some point t, and then e to the minus s. Now, the first thing that I have to do is integrate out the fermions. And if I integrate out the fermions, I get fermion propagators. So this guy, together with this, will give me the inverse of the Dirac matrix. And this guy, together with this, will give me an inverse of the Dirac matrix. And in addition, I will get the fermionic determinant into the game, which it's already there anyway. So if I work out this expression with the rules of the U integration because of the fermions, I will get the determinant of d plus m, which is my two-flavored QCD has 2 copies of this determinant. And then here, what I have is the trace of, and I will define S as the inverse of D. And I have an S that goes from 0 to T, and I have a gamma 5, and I have an S that goes from T to 0, and I have a gamma 5. So that is the 2-point correlation function for the pion. So the interpretation of this is a creation of a pion at some time t, and then the annihilation of a pion at some other time, at some, okay, so create a pion at t equals 0 and annihilate a pion at t equal t. Okay, so now what can I learn from that pion, from that 2-point function? So if you look at this 2-point function, pion 2-point function, as we said, it created the pion at some initial time and annihilated the pion at some final time. So you can understand what this 2-point function is by looking at the spectral decomposition, as it's called. So you have O, you have the creation of the pion at 0, and you have O and the annihilation of the pion at some t, and this is t, and this is O. So you can actually introduce a complete set of states in here of, and I will write them by n, so which are all possible states with the pion quantum numbers, which are normalized by the energy n, sum over all n. This is the identity in the pion sector. I'll put a p here. So if you introduce this complete set of states between the 2 operators, and also translate the operator O by OP of t, if you translate it, is e to the IH t OP of 0, e to the minus IH t. So this is the time translation of the operator t to the origin of t equals 0. So if you do that, and in Euclidean, in Minkowski space, then the 2-point function of the pion is going to be given by the expectation value of O acting on a pion n, and then you have e to the I e n t over 2 e n, and then you have pion n O dagger O, and then sum over all n, where n are the energy states. So if I define Zn as my overlap factor of this matrix element, which is the vacuum, this O annihilates the pion, it creates the vacuum. So this is a complex number, and Zn dagger is the other way, O dagger on 0. So the 2-point function of the pion can be written as sum over n e to the I n t over 2 e n times z n z, I don't know, star, let's say, because this is a number, z star n. So this is the pion 2-point function, which is basically like the time evolution of a quantum mechanical particle of energy n, but we now have the possibility to have multiple energy levels, so each one of them has its own energy factor. Now, if I go to Euclidean space, then you have t going to minus I or plus I tau. In this case, the pion 2-point function in Euclidean space is going to be a little different. So I'll have sine over n, I have Zn star e to the minus e n t divided by 2n. So we have this beautiful thing that the oscillating exponential has turned into a decaying exponential. So the decaying, this is beautiful because it allows us to isolate the ground state of the pion. So if I take the limit of t going to infinity of the 2-point function of the pion, this only the lowest energy state will survive. I'll put 0 star, and the energy of the lowest state in the channel of the pion is the pion, the mass of the pion. So this is m pi times t. So in order to calculate the mass of the pion in lattice QCD, I have to calculate this 2-point function of the pion, which involves us to sample the weight of the QCD action, which I have e to the minus s here. I have to sample the weight that the lattice QCD action is giving me with the Monte Carlo method, and evaluate this trace of the two quark propagators between 2 points, a point at t equals 0 and a point at larger value of t. And if I do that and observe the signal for sufficiently large Euclidean time, then I will have the exponential decay that looks like the pion mass. And if I want to be schematic, and I can make a plot here of the 2-point function of the pion in logarithmic scale, you will see the following picture. And there would be error bars because it is Monte Carlo simulation that I have done, and I have expectation values. And if I look at the large separation you will see that in log scale, they will be approximately linear. So this is log scale. And the slope of this line would be the pion mass. So this is how you would calculate the pion mass in Lattice QCD. And I forgot here to write 2m pi. This is my denominator that was there to begin with. So all I do is do this calculation, take the log of this, fit the slope, and you get the answer. Now, of course, this is not robust numerically, so you would do something better. And there are two better things you could do is, first of all, you take the 2-point function of the pion, and our pion goes up here. This is 2-point. And you calculate what is called the effective mass of T, which is a ratio of the 2-point function at some T divided by the 2-point function P of T plus 1. So if you plug in the expression that I have up here into this, and you do the algebra, you will find that this is really, if the ground state is dominating, which means that at the limit of T going to infinity, you will get m pi. So this thing, because the numerator, and I can calculate if you want, the m effective of T is e to the minus m pi of T times some amplitude divided by the same amplitude e to the minus m pi. And I have to take a logarithm here, sorry. M pi T plus 1. You take the log, and the amplitudes go away, so you get e to the minus m pi plus, and then you take the log, and then you get m pi. So at the limit of large T. Anyway, the other method that you could use in order to get the mass is going to just do a fit. So you can take the pion 2-point function and assume that is given by an amplitude e to the minus m pi plus another amplitude e to the minus, I'll put a prime here, t, or and assume that you have two exponentials and you do a fit in a window of time, in a time interval where this model seems to fit well, and you extract the lowest of the two masses. That's another way of computing the mass of the pion. Now, the pion is nothing special. Any hadron state that you want to compute its mass it's going to work exactly the same way. So for example, if I want to calculate the mass of the nucleon, so I need to introduce an interpolating field of the nucleon. So the nucleon is a spin 1/2 particle. It's a spin 1, it's positive parity and spin 1/2. So I have to somehow build a spin 1/2 object out of my quark fields. But this is the J quantum numbers. The proton has isospin 1/2 as well. So I have to also be mindful about how I combine the flavors in order to get isospin 1/2. So I can write down an expression This is A, B, C. This is the Levi-Civita tensor. I have to create a color singlet. For the pion, the way that I wrote it, psi bar or U bar D, I had the contraction of the color indices implicit, and that was a color singlet object. For the pion, for the nucleon, I have 3 quarks. It's more complicated to write a color singlet, but you can achieve it by using the contraction by the epsilon symbol. Is it only 5 minutes? Okay, fine. Okay, good. C gamma 5 and DC, where implicit sum of repeated indices are involved, and then this internal, I will put an index alpha here. So let's see what these indices are. So the spin indices are contracted here. Okay. Come on. Now that I have a little time, I'm going to be B transpose B. Okay, so the spin indices are contracted in here. There is a spin index that is left over that is going to be the spin index of my nucleon. And the color indices ABC, ABC are contracted with the epsilon symbol, and that creates a color singlet. So the nucleon is a color singlet. Now, if you look at the flavor content, it is up, up, down. So this is an antisymmetric combination because of the BC symbol here. So an antisymmetric combination of isospin 1/2 objects creates an isospin 0. So this thing has isospin 0. And we are left with the isospin of the up quark, which is 1/2. So in terms of flavor, we have the right flavor quantum number. Now, in terms of angular momentum, the spin indices are contracted here. So this is a spin 0 object. So you are left with the spin structure of the single quark. So this is a spin 1/2 object. And if you care to calculate the parity transformation of this object, you will find that it is positive parity. So this is an interpolating field that generates the nucleon. And I would, if I wanted to compute the mass of the nucleon, I would do exactly the same thing as I did for the pion. The difference is that I now have 3 quarks that I have to worry about. So if I wanted to calculate the mass of the nucleon, I would compute the 2-point function of the nucleon, which is C nucleon 2-point of T. Now, you will see that you will have now 3 different quarks that to worry about. So you will have to contract 3 quark propagators in order to create the nucleon. And the other thing that you will have to realize is that if you put it inside the path integral, and which is d psi bar du, you get now u, and I will be schematic. I will drop all the indices. C gamma 5 U D, and then you will have U bar transpose C gamma 5 D bar, and this is at T, and this is at 0, and then e to the minus S, the gauge, the QCD action. But now you realize that you see that there are multiple up quarks, so you can contract this guy to generate. And then you can contract these 2, and then you contract these 2. But now you can have the additional contraction that this guy goes there, and this guy goes there, and the D quark remains the same. So you have 2 diagrams. And I can write in a more schematic way, and then let's call this the down quark. So you have one quark propagator that goes the down quark, then you have one contraction. Now, because you have fermions here, and if you do the other contraction, it means that you have to compute to commute two fermions. Then this comes with a minus sign. This guy contracts there, and this guy contracts there. So these are the two diagrams that you have to consider in order to write down the fermion, the nucleon two-point function. Now, the analysis for getting the nucleon mass is identical with the analysis that I described on the case of the pion. The only difference is that if you make a plot of the nucleon two-point function, then you will see that the mean values will do something similar, but the error bars are going to be different, and they are going to grow as you go to larger and larger distances, but a single exponential will emerge at long time separations, so you can get the nucleon mass. This is Mn is the nucleon mass. So since I'm out of time, I will stop here. And so tomorrow I will discuss the computation of observables that have to do with hadron structure. And see you tomorrow. Questions or comments?
It seems like lunchtime.